particle physics did themselves no favor that what counts as a fundamental discovery in our field is basically discovering a new particle. There is no other field that thinks like that. There is no other science that works that way.
Yeah.
It's nobody in astrophysics expects to discover dark matter directly with the next telescope, or to measure something for sure that has never been seen before. We have a kind of double standard there.
What's up, you scholars of enlightenment? Dr. Sam Gregson, particle physicist here again. I hope you've had a brilliant week and have a fantastic weekend in store. Now, today's topic is particle physics in crisis. It's a claim that we hear regularly, not only from high-profile online influencers, but also scientists inside and outside the field. Many insist that a new mega collider cannot be justified. Others contend that fundamental theoretical physics is stuck in the mud and has made little progress since the 1970s. Still more worry that particle physics is suffering from a PR problem and structural issues inside the field that will stop it from attracting and retaining the brightest minds in the decades ahead. This crisis seemingly takes many forms and is multifaceted. So is the end of particle physics nigh? And is the field really in a state of crisis? To help me wrestle with this issue and understand the current status of particle physics research, I'm joined by three brilliant special guests. Firstly, Dr. Vladimir Gligorov. Dr. Gligorov is an experimental particle physicist working on the LHC-b experiment at CERN and the Large Hadron Collider in Geneva, Switzerland. His work focuses on CP violation, the mystery of why our universe is dominated by matter over antimatter, and flavor physics. He is also an expert in experimental trigger systems, hardware and software that identifies intriguing signals in frequent and fleeting particle collisions and saves them for future processing. I'm also joined by Professor Cliff Burgess. Professor Burgess is a theoretical particle physicist. He is an associate member at the Perimeter Institute with a joint appointment as a professor within McMaster University's Department of Physics and Astronomy. His research focuses on string theory, phenomenology, and cosmology, and particularly the interface between string theory and lower energy physics, with an eye on how the ideas arising at that interface can help with open questions in particle physics and cosmology. Last, but by no means least, I'm joined by Professor Martin Bauer. Professor Bauer is a theoretical particle physicist based at the University of Durham. He has studied the Higgs boson, dark matter, and flavor physics with a focus on phenomenology, and has a keen interest in the detection of new light particles with colliders and quantum sensors. He is also a science board member for the Science and Technology Facilities Council in the UK, which oversees fundamental research and its funding in astronomy, physics, computational science, and space science. So I couldn't ask for three better guests to help me dig into the alleged crisis in particle physics. So, guys, many have claimed that particle physics is in crisis, and I want to break that contention down into four rough areas of concern tonight. So, firstly, the claim that particle physics is kind of coming to an end, and with the completion of the standard model, the field is kind of winding down. Secondly, the suggestion that requesting funding for new super colliders is unjustified. So whether or not you want to do precision studies of the Higgs or jump forward in energy, we need to be able to justify that. Third crisis idea is that fundamental physics has stalled over the last few decades, which is what a lot of people say. Theorists are lost in math, they're lost in complexity, and they're not solving the big problems. They're still the same as they were in the 70s. And then fourth, the crisis that I see kind of thrown around is the belief that particle physics kind of has an image problem. And with that are some structural problems in the field, which I know Varvar is very passionate about, and rightly so. And that hinders particle physics as a field from going forward, unlocking funding and attracting the best and brightest. So I want to cover all of those problems tonight. But before we do, Martin, I want to come to you first and ask you to put this idea of a crisis in particle physics in a bit of a historical context. So I was looking at a Twitter thread that you did last year where you discussed this idea of a crisis in particle physics. And you mentioned that you'd read a more than 100-page strong article in a research policy journal entitled The Crisis in Particle Physics. And that article made many of the same damning accusations about particle physics that we regularly hear in contemporary media. So particle physicists are happy to sacrifice simplicity for progress. Theorists are too into speculative ideas. They're too stuck into maths and not solving the big problems. The crisis has been ongoing for many years. What was this policy document and why did you find it so interesting when talking about this problem of a crisis in particle physics and setting it in a historical context?
It's as you have on the screen. It's a paper basically written for a research policy journal back in the 70s by a physicist who's also, I think, a social scientist, Michael Moravcik. He has written quite a bit about the impact on science, and in general, he's written a couple of books as well on the topic. And because he was a high energy physicist, he is focused on that. And I think in that context, this document came about. And the reason why I wrote about it is basically that the idea of being in a crisis always sounds, in a field like high energy particle physics or in any scientific field, well justified from the point of view of the people that consider themselves in the crisis. Yeah. But if you go back in time, you will find people basically at every stage that have considered the current situation to be a crisis, no matter what we would call it today. And I found this particularly remarkable because it fits right in the time frame that is being held up as the golden age nowadays.
So this is 1977, right? So this is just after kind of
yes,
QCD and lots of discoveries just before that. Please continue.
The Standard Model, again, to solidify, at least from a theoretical point of view, showing that it's realizable, that W and Z must be there. And on the QCD side, there was a picture emerging behind these resonances that was satisfying to some degree. At least it was much better than it was in the 50s or 60s. So it is a time that is being shown to students nowadays as the golden age, where particle physics was fun to be in, and where you had a discovery basically every other week on top of a good theoretical picture. There was theoretical progress as well. But that's not how everyone perceived it back in the day. And there was a minority of people, including Michael Moravcik, who wrote this paper, that had strong criticisms about the way experiments developed, about the way theorists approached the problems of the time. And that's not unique either. Like before that, in the 50s and 40s, there was the crisis of infinities in QED. There was no theory that made any mathematical sense. People were dissatisfied with that. People were dissatisfied with quantum mechanics. There was a crisis when the ether wasn't found to explain the speed of light. So there was a lot of phases in physics where, if you look back and what people actually wrote, you will always find some people that have considered this to be a terrible crisis, but where the view has changed as soon as the issue was resolved.
So potentially, it's easy to see the current period as a crisis when you're in it, but it's hard to contextualize it kind of after the fact, right? It's very easy to say that we're in a crisis, but you can't see it in the context of the wider picture. And this has happened many, many, many times throughout history. I guess that's the main takeaway message, Martin.
Yeah, I think if it was a situation that we have encountered before, like a crisis we have seen before, we would know how to solve it and wouldn't call it a crisis in the first place. We're usually pretty good at stepping through these challenges. But as soon as you're in a situation where the things that you have tried before didn't work out of the box, you can be fast in calling it a crisis at some point, because at that point you don't see what the solution is. A couple of years later or decades later, this might look different. You might still call it a crisis looking back at the people who did it, but once you're through this point, you're at the next crisis and you have to solve that problem. So I think it's a bit tricky to hold up a point of view that this is like a unique situation because it's a crisis, unique because we don't know the solution yet.
So that doesn't mean that criticisms or improvement of the field are, not welcome, or discussion is not welcome. But there's not necessarily anything special about our current period, right? Science is a perpetual crisis where we're always trying to move forward. So seeing this as a particularly special period might not be a particularly useful window. So I want to come on to the first idea that I see people mention when they talk about a crisis in particle physics. And that's this idea that particle physics is kind of coming to an end. It's winding down. So Varvar, maybe if I come to you next, I'm going to try and give everyone a kind of equal amount of time. It might seem like a silly question to ask, especially given the many paths that were laid out by the P5 report just before Christmas. But many serious articles, serious individuals seem to be kind of saying that particle physics is winding down. It's coming to an end. We've found most of the things we need to find. What are your thoughts on that contention, Varvar?
So, okay.
Because I know you've written quite a lot about this, I know.
Well, I think you can. I think a lot of this depends on where you're looking at it from. So if you're looking at it from the perspective of the last 40 years, and the best and brightest experimental minds in the field are now telling you that are now making timescales for the next 80 years. Of course, it's very easy to, and I'll elaborate on that in a second, it's very easy to get a reference frame in which it does look like things are slowing down, elongating, and so on. If you take a step back and you look at where humanity's understanding of fundamental science was 150 years ago, I mean, you can only be amazed at the overall amount of progress. And then what's happening today with respect to where we were 30 years ago looks like a little tiny blip at the end of a kind of exponential upward explosion. On the other hand, knowledge does go in plateaus. So you can have periods of rapid growth, and then you can have periods of stagnation. So it's not like we can deny the possibility that because we've done this amazing work, because the field and all these intellectual giants have put this dynamo model in front of us, which describes, we know, microscopic reality on a very wide range of energy scales. Sure, the next energy scale and the next theory. I apologize for my dog, by the way, but he's very jealous.
Okay,
so I have to check him while talking to you. I'm sorry about that. The next theory, next energy scale could be far away. It could be further away than what we would like in terms of our capacity to experimentally probe it. These things are all possible. So those are two reference frames. There's a third reference frame, though, which is of the people kind of doing it. And I think when we talk about crisis in particle physics, this feels very different if you're a theorist or an experimentalist, I think. I'm not a theorist. Not sure how it feels from the point of view of...
We'll get to the theory, don't worry. The theorists will have plenty of time to talk.
However, if you're an experimentalist, things are now different than they were during the golden age and what came immediately after it. If you were a PhD student who graduated time W and Z boson were discovered and were kind of caught up in the field because of that, you had to wait fewer than 10 years for the number of neutrino species, fewer than 10 years after that, actually more like 5 for the top quark, fewer than 10 years again for the KM mechanism, and in between there were massive discoveries about neutrinos as well, and a whole host of other small experiments around the world doing super valuable stuff with charm and beauty physics and so on. And then fewer than 10 years later, essentially, you had the Higgs boson. So now we're 10 years on from the Higgs boson. And the same collider delivered the Higgs boson were meant to finish its full exploitation 20 years from now. Well, again, going back to the previous period, there were multiple colliders on multiple continents doing super exciting stuff. So the fact that the field has centralized around CERN is, I think, undeniable. For an experimentalist, that does change your life. It's in particular collider physics. I mean, of course, then you have a whole plethora of smaller dark matter experiments and all kinds of smaller experiments.
So there's still a lot of work that needs to be done, though, right?
They're still around.
Neutrino mass, dark matter, dark energy,
Sure,
Y3 generations. Why is the Higgs so light? There's still an awful lot of experiments people can work on.
There, but the fundamental questions are there. The difference is now, absolutely, the fundamental questions are there. But the difference is now, nobody can promise you that by the time of the full exploitation of the LHC, you will have made progress progress in the sense of discovering something, what other people like to call discovering something new. What we can guarantee is we will probe known nature to unprecedented precision, which I personally think is super important and absolutely necessary to do. But it's not the same thing.
Yeah.
And then you have, and then your next collider is going to be another 10 years. So that's why in the 30 years, that's why I put this reference frame in the 30 years from the discovery of the W to the discovery of the Higgs versus the next 30 years. If you're an experimental, it just does no good to claim to the current generation of experimentalists that, oh, well, we've seen this type of thing before. That's not true. Now the planning is extending not even on the timescale of professional life, the timescale of a human life is not the same. And I think at that level, the field internally, I think there's a bit too much glad handing of my generation that's going on. And, people are not stupid, they understand. Doesn't mean the pursuit isn't worthwhile. I think it's extremely worthwhile. I think we're obliged to measure the Higgs with incredible precision. And we're obliged because it's a fundamental object at the heart of nature. Otherwise, why are we here? But selling it is kind of more of the same. No, that doesn't wash.
Yeah, and I think we're gonna come on to that. No. I think these are all really good points, and we're going to come on to that idea of the kind of structural problems we have in the field, and the kind of how the field looks to people inside and outside. Cliff, there are still a lot of open questions though that we need to answer. Right, this idea that the kind of particle physics and theoretical physics is winding down it seems a little bit, well, just very naive to me, because there's still a lot of open questions, aren't
there? I agree with that. I'd like to comment on what was been said before, too, because I'm old enough that I started graduate school in 1980, and so I lived all these things that you're talking about. And so the perpetual crisis is absolutely true. I can remember, as a graduate student, I remember we were all in Weinberg's office for a group meeting, and he got the call or something saying that the W had been discovered or something. So that was exciting. But then after that, from the theory point of view, it wasn't like every few years something marvelous happened. It was the standard model wins all the time. And we had to wait for LEP for 10 years. That was so boring. And then we had to, and LEP, because it was wonderful what was done at LEP, but it was always the standard model that was winning. And then the SSC and the LHC, that was a long process. And so I think it's what's true, the crisis has always been around, but it is true that we're in a time frame where we're in a situation where the time frame for colliders specifically has gotten super long. And probably the biggest change that I've seen there came with the canceling of the SSC, in the sense that we don't have any competition anymore between Europe and the US, for example. So I think that's part of what's made the timescales long. And I'm hoping that the Americans kind of regain their ambition, because they're doing good things, but they used to want to do good things in all areas, not just some things. And so it's hopefully that's I think that's it. If the time frame for experiments is going to be 30 years, then we're going to lose the experimentalists because they're going to do something else. But from the point of view of physics to do, a lot of these discussions are really hinges on what you think particle physics is.
Yeah. Do people over focus on discovery machines and then forget about neutrino physics that's being done? Vava, yes. I know you talk about dialing in the corners of the unitarity triangle, things that we definitely need to do, but people don't necessarily see that in the same breath as we're going to smash things together harder and go up in energy. Cliff.
But I can remember the whole story of neutrino oscillations. That was a surprise. And it took about 10 years for people to be convinced, from nobody understands the sun that well to really the oscillations are there. Dark energy was a big surprise. People started to get inklings, but then it kind of came And on the theoretical side, things like, I think people like to dump on string theory, but I think ADS CFT was an enormous theoretical step forward that was a huge surprise, that there's way fewer field theories than we thought there were, in a really remarkable way, that that what you think space-time is can look really different if you look, depending on what you're looking at. A whole bunch of things have been happening, and I think the whole discussion about is particle physics over reminds me of we had a panel discussion once about dark matter, and one of the questions was, what will happen if the solution to dark matter if it's a non-particle physics solution? And I remember thinking that, whatever the solution is, that will be particle physics, because we're gonna, if it's something else that you don't call particle physics now, we're all gonna move into that, and that'll be particle physics. So I think from the theoretical point of view, colliders are great, and we need them, and I'm glad that they're doing all the tests. And if they keep verifying the standard model, that's information that we can use. Yeah. But astrophysics has got all sorts of other cool things that we have to explain, and the same thing's true for neutrino physics. And so there's a lot. Particle physics to me is the interface of human knowledge with nature at its most fundamental level, and where we get the evidence for that experimentally doesn't have to come from any one experiment. And so I think the field is going to thrive, and it has been thriving even through these long, lean times.
And Cliff, you kind of alluded to something there, and this is something that came through strongly in the P5 report, was that this new frontier between particle physics and cosmology, which has become more of a precision science, is becoming a very rich area for research, isn't it?
Absolutely, yeah, and that's not even new. I mean, I can remember people consciously in the late '90s thinking, well, I've got to start learning some cosmology, because a whole bunch of things are going to be happening that are going to be very precise, and you can't just make shit up anymore, which is what the joke was at the time. And so, I think that there's opportunities all around, and you think that 95% of what's in the universe, we don't know what the hell it is.
Yeah.
The astronomers will tell you that it exists, but the people who tell you what it is will be the particle physicists.
So
I'm not worried.
So there's a hell of a lot of work to do. Martin, do you think maybe part of the issue with this idea that particle physics is kind of coming to an end is how we sold things at the LHC, and obviously the Higgs boson? When I can bring up this the next picture, the Higgs boson is obviously the last piece of the puzzle in the standard model. So for other people outside with the LHC, they see maybe a faux picture of finality, the model being finally put together, the standard model continuously winning out. Do you think maybe the public and people even in the field get this kind of faux idea that we've reached a kind of finality in particle physics and a kind of a dead end with the completion of the standard model?
When I talk to people that you would call the public, that are not physicists, I don't get that impression at all. Okay. Most of the time, there's a lot of enthusiasm and a lot of questions about this. I don't think this is the issue. I think Cliff put the finger on the wound, basically. I think the main issue is competition. The LHC is not only the biggest project, it's also the longest running project, and it's planned to run longer than all the other machines that have been built before it. And the main reason for this is this the only option at the moment. We started way too long. This is a mistake that particle physics made, or collider physics more narrowly, if you will. It took way too long and still not decided yet what the next project is going to be. We knew these timescales would be long, and whenever we start, we should have started much earlier. We should have started once the Higgs was discovered. We should have started to basically make up our minds, go to politicians and tell them, listen, this is the big success of the LHC. This is going to be the next project. It's going to be harder and harder to convince people that this has to be built and to stay in the field if you wait so long. The BAFA is completely correct about this. You can't sell well to young people to get excited for a project where they will be close to retiring when you get the first data.
Yeah.
So that shouldn't be happening, and I don't believe this is the fault of the next collider is going to be built. This is a political decision. This is mainly to do with the fact that the SSC was cancelled. When I was in the US as a postdoc at Fermilab 10 years ago, in the SNOMES process, there were senior people that literally said the last thing we want to do is ask for another collider. And the main reasoning was frustration and basically on the back end of the fact that the SSC was cancelled. That has really, really hurt the psyche of American experimental particle physics. And I think this generation is about to overcome that, but it took a long time. And we see the consequence of this now. This is the main reason why it will take so long. I don't think public support has been stronger in the past. Not at all. I think there's a lot of support, and even from other physicists in general that are interested in particle physics, maybe indirectly. There's a lot of support, but I don't think it was a good decision to wait so long before we make up our minds what the next project is going to be.
Fair enough. So wrapping up this section, we'll bring back the scary slide. Is this a real crisis? The idea that particle physics is coming to an end. So we're going to do a scale from 0 to 10, where 0 is no crisis whatsoever. 10 is the sky's falling. Vava, out of 10.
5.
Martin.
It depends what you mean by the sky is falling. It's hard to say, because when you say the sky is falling, it basically sounds
the
like
theorist for you.
Yeah. Quick game's a good quick game's a good game, Martin. I'm going to have to push you.
Yeah, then put it at 6.
Okay.
I'm a perpetual crisis. I think this is a good model.
0.02.
We're going to go 2. Cliff's slow. So we're low to moderate on that one. So I want to move into the second one, because I think, and I think we kind of alluded to it there. This is the big thing that I see a lot of people discussing when they talk about a crisis in particle physics. It's this idea that scientists should not be requesting funding for a new super collider. And Vava, you kind of mentioned it or alluded to it already. Should we build a bigger collider? What is the use case? I guess in the short term, it's a lepton collider for precision studies of the Higgs, right? Vava.
Is it me?
It is you.
Well, I think we should reframe the question. I think we should ask ourselves what fundamental property of nature do we actually want to measure next?
Yeah.
And I think the obvious answer is we want to probe the Higgs in as much detail as possible. It just so happens to be the case that very conveniently, any plus E minus collider, which lets you do that, also lets you probe a whole bunch of other properties of nature you care about with a great deal of precision also. So that's great. But then you have to face the problem that we've framed this discussion completely wrong, and we keep doing it. First of all, the financial cost in this respect only sounds scary if you let it sound scary. I mean, 100 billion, sure, that sounds like a big number. It isn't actually a big number over the timescales, number of countries involved. It's actually a fairly small number. By far, the bigger challenge is the one that Martin alluded to, and also Cliff, up to a point that, look, you need to do this in a way that that means the experimentalists have a community, and a community that sustains itself. You know, one of the most rewarding things about being an experimental scientific physicist is the number of incredibly intelligent people you get to work with on an everyday basis, which is something that is very hard to replicate elsewhere, because for decades the field has had the best and brightest flocking to it. But if you want to sustain this, then indeed, I don't want to bang the drum every time, but then the timescales do start to bite. So the question is not just what does it cost in terms of money, but in terms of money to do it on a time scale that actually delivers you what you want. So the real question is, you know, okay, so FCC, sure, but what's the FCC for? The FCC is not just for probing the Higgs. The FCC is an infrastructure project to give CERN a long-term future. So it has that aspect too. And that's actually by far its biggest advantage over the ILC. There are scientific advantages too. But the biggest advantage is that ILC from an infrastructure point of view is perceived as a road to nowhere. Of course, these discussions, I mean, you have them over coffee at a conference with colleagues, and people nod and so on. But this is kind of the problem, is that the things have gotten mixed up at that level. I mean, when you act, so then sure, everybody's favorite collider has some advantages over the other ones, but having any other collider, E plus E minus, in parallel with the LHC would be, you know, enormously beneficial to the field compared to what we're being offered, which is run the LHC into the ground, and then you'll get an E plus E minus machine afterwards. And that's why I say the framing is, and this also cannot be disconnected, by the way, from the fraction of people, from the high turnover model the field runs. So when we talk about, we are asking the public to build us a new machine, but we're also again asking to sustain the community. And really, if we wanted to go faster and build more things in parallel, we would have to ask that a far larger fraction of people that we train get a chance to stay in the field and have a career in the field, a fraction which has plummeted over the last decades without any doubt. The statistics on that is clear. And of course, that mirrors wider trends in society, but that doesn't help us here. So that would have to be an ask. And that, what I, to wrap this up, and so I think that the reference frame where this constantly gets pushed into this financial cost of essentially what will be the tunnel and so on, I think is a reference frame in which you can't have the real conversations that you would need to have to break out of this impasse.
What would be the use case though, Vava, in terms of the science? So if we were to say, you know, we want to build a new collider, what are the next things we want to be looking at? Why are we building that E plus E minus collider?
I don't think you need more justification in the Higgs. I mean, I think look, the way I see this is to me is very simple and maybe is simplistic, but we have this incredibly fundamental object, and if you know, and it's actually it is remarkable if you think that you have this field that permeates everywhere and through interaction, you know, gives things mass and so on and so forth. When I go talk to high school students, for example, about this and so on, it always provokes amazement. And of course, you want to understand this object in all its detail because it's so fundamental that by doing that, you're going to indirectly learn, right? And the story that we can tell about how indirect precision measurements guide us towards eventual direct discoveries, you know, I'm not going to bore Martin and Cliff with that because they know it far better than me, but it's rich and it's very simple to tell, and it holds up. So then I don't personally think that you need more of a scientific justification, but then of course it can do other things as well. You can do electron, you can do electron ion collision, you can do all kinds of things. You can, I mean, once you start, you can turn it into much more than what you started with. That's also, by the way, been a theme with colliders. The LHC discovered the Higgs, but all the LHC experiments have found very innovative ways to do stuff with the LHC that was not there when it was first done. So once you build the object, but as I say, but I just think unless we are able to change the reference frame in which this gets discussed with policymakers, I think we're going to get stuck into, now we're just doing European pork barrel politics. The SSC was doing American pork barrel politics. So the SSC failed. Hopefully this will succeed, but that's not you want to be doing something else, I think.
So Cliff, I guess we kind of, and Vava kind of push it there, is we kind of owe ourselves at least one more collider, an E plus E minus, or some kind of lepton collider, to study this amazing object, this Higgs that we've discovered. What is the theoretical case for looking at the Higgs boson in exquisite detail with a new lepton collider? What are the most important things that we want to find out about the Higgs boson, Cliff?
Well, I'll come back to that.
Please.
But, I think that we're not owed anything. I think that there's a cost effectiveness case that needs to be made if we're asking about making colliders or any large infrastructure in science. And the government has got money to spend on other things, and I want them to cure cancer too. I got a stake in that, and so it's that nobody owes us anything, and so I think that we need to make a case, and the case gets made at many levels. I think that what makes these discussions hard is that there's several different kinds of arguments that are all kind of mushed together in the same discussion. And one of the discussions is, as scientists, we need to ask, so given some amount of resources, what's the best value for money? So what would we really, and I think that normally does not mean one thing. That normally means, we don't know what the answers are. And so we have a kind of a risk portfolio we're trying to run, where it might be that we need higher energies. It might mean that we need very precision measurements, and we probably need all of them to really get a sense as to what's going on. But then there's always trade-offs. If you spend a lot of money on this, you can't do this. And I think scientists should be assessing the scientific benefits of all these things so that we have priorities. And we won't agree them all, but it's important that we kind of coalesce behind some broad priorities. But when we make the case to the governments, they don't care if we quantize gravity or if we figure out what the Higgs is. They are spending the money. I think we need to understand what motivates them when they fund us. And what they're funding us for is not because of the science we're doing. I think they like the science, but that's kind of a side effect. I think they're funding us because they see this as a way, we draw people in who are attracted to learn mathematical problem solving skills or practical computing skills or big data skills because of the cool ideas that we're thinking about. But then most of them don't stay in the field and they go out and they do other things, like they have startups and they make Googles and they make Apples. And so we got to be very careful if we make the case that we really have to have a lot more people stay in the field. And that's going to be important for the funding of it, because that's exactly what they're not trying to have us do. And so, the case we want to make is that we're doing dynamic science. We're going to spend it really well. It's really worth your money. You spend $100 billion over 10 years or whatever the budget is, you're going to reap way more than that because of the human capital that you're going to get and the World Wide Webs that'll be spun off on the side. That's the case we have to make to them, and it's a different case. But they have to be sure that we've decided that our scientific priorities are in line, and so that if they're going to spend the money, we're not going to waste it.
Yeah.
Now, as far as I think I completely agree that there's lots of physics in the Higgs to be seen. I think there's lots of physics not in the Higgs to be seen, and I think probably the important thing about making an E plus E minus machine is multi-purposeness. So it's like when you're sending a space telescope up. Maybe you want to use it to measure dark energy, but you also like to be able to do a lot of bread and butter astrophysics because you want a big community to buy into it. And so things, I think all, these collider proposals that are being made, the Higgs is probably what I'd be interested in, but there's lots of physics that can be done. And I think the more we build things with a view that we can use them in a multifaceted way, the more likely we'll be to get people behind them and then be able to sell it to the politicians. That makes sense.
Vava, you'll get a chance to put your political prescription. Don't worry, I've got that in later on with the percentage of PhDs and things like that. Don't worry, that is there, and you will get a chance to go with it. So, Martin, how can we sell that to the politicians in terms of a science case, in terms of a use case, then of having this E plus E minus? What do we think are the most important things we want to discover about the Higgs? What are we looking for in the field so people can understand that if we build another E plus E minus machine?
You will find different answers to that depending on who in the field you ask. But there are some obvious answers. We want to know the Higgs potential. So far, we have basically only measured its mass and the biggest couplings that were accessible at the Large Hadron Collider.
Yeah.
But we don't really know whether it's the standard model Higgs unless we have any idea of how the Higgs talks to itself, what the Higgs potential looks like. Which is in the end responsible for electric symmetry breaking, the whole mechanism that was that brought a Nobel Prize for Higgs. So that's what we want to learn in the first place. This is, in my opinion, the most important piece. And then obviously we want to understand how the Higgs interacts with the other standard model particles that are too hard to see or to find within the data at a hadron collider. So an E plus E minus collider would help a lot. There's also about 10% of Higgs we produce. We don't know what they decay into. We have no good handle on the width of the Higgs, which basically is the sum of all its possible decays. And for some of them, we can't account for them. We don't know what they are. So that might well be something we don't expect. And there's only one way of figuring that out. So the Higgs program is by itself extremely rich and worth building a new collider. And beyond that, I often try to describe it as a theory, the standard model that lives in two phases. It's like ice and water. Imagine you have a physical theory that can describe perfectly well how ice works, but it also predicts that there's a phase in which it behaves like water. And you wouldn't set out to test that. It would be a pity to leave the standard model untested at higher energies. So that, I think, is a good argument to build, for example, the 10 TeV muon collider if we were able to do it. I also want to comment on a few things that were said
Please do.
Before. One of them, the things that politicians worry about or care about with regard to science. I think Cliff is absolutely right that there is no one science case that will make them excited. But what will make them not excited and give them an easy out to strike things down, no matter what they are or how well motivated they are, as you saw at the SSC, is if there is not unity. If you can see that within the community that's look for something, there are many different opinions, and people point in different directions, and it's unclear what they really want, then you won't get the money for sure. It's almost guaranteed. There's also a fact that scientists often overlook because it looks so unintuitive, but science funding isn't a zero-sum game. It's rarely the case that you have to say, oh, we don't build that, so 5 years down the line we can build that. Or if we invest that in particle physics, maybe we can't build a telescope next. I'm at the science board, as you know. This is one of the boards that recommends future projects to STFC, the major funding agency in the UK that's responsible for particle physics funding. And more often than not, you're in a situation where smaller fields or other fields can piggyback off a bigger project or get funding for things that would have never been funded if there wasn't some bigger goal to work towards. And same for the situation that the US or Europe builds a particle collider. If you build one here, it's, in my opinion, more likely that a future project will be decided over the Atlantic. I think these things, competition and in general bigger projects, help building other bigger projects more likely than not. Bauer is also absolutely right about his comment about the money. It's always crazy when these big sums are named, but science was always expensive on that level. In fact, if you compare the numbers, it's not necessarily more expensive than it was back in the day. So if you wanted to build a lab in the 80s, you wanted to take the money from the richest people in the world, you would have needed to confiscate the money of like 5 or 6 people to fund that. Today, if Elon Musk wakes up and decides not to buy Twitter, he could build the FCC by himself and probably wouldn't even realize that the money is gone. The times we live in is certainly funding available for giant projects if you decide to do them. But this is something that needs to be, that case needs to be made in an aggressive and ambitious way. If you go to politicians and say, this is our 80-year time frame, they will react the exact same way as an experimentalist who's sitting in this experiment and thinks about their future. They want, ideally, something to be done within their period of legislature, like 4 or 5 years, which won't happen. But even beyond that, they want to fund projects where people can see when they happen. They don't want to fund projects where it's far in the future. There might be something down the line, maybe next century. I think this is the dangerous part about this. And this is to some degree our own fault. We need to be more ambitious and aggressive with these proposals. Otherwise, they won't be happening, I think.
So we have a kind of use case for an E plus E minus collider. You know, we've discovered the Higgs. We have almost a duty to look at it in detail. I think where some people get upset or they say that there's a crisis is when you then talk about jumping up in the energy scale. So you talk about a future circular collider HH, so a bigger Large Hadron Collider, for example. Cliff, is there a use case for building another discovery machine that goes up 1 order of magnitude in energy? You'll see people saying things like, for example, you know, we have this desert just above where we are now. We have no reason to expect there to be new particles, new forces from anywhere, or we know of no reason for there to be from here up to the Planck scale, or at least the gut scale. What would be the theoretical case or the use case for another discovery machine? Is there one, or is that a difficult case to make, Cliff?
Well, I think it's no more difficult than it ever was. You know, that the case against it that you just made is a really bad one, in the sense that
I saw you discussing this on Twitter, so I set it up, exactly. And I know you think it's a bad one. So away you go.
I thought I was being baited here.
You were being baited, and you noticed. So well done, well done.
But you know, I think so. I'm rising to the bait, and so I think the honest thing is no one has any idea what's going on above the Standard Model, and it could very well be there's stuff right around the corner. It could be there's a desert. We don't know. The point is to find out. and I think that's the case, is that we should never be in a situation where we have to prove that there will be a discovery in the next decade of energies in order to build the machine, because then we've discovered it already. So the whole point of the exercise is to go through virgin territory. And so then you can argue about what are the motivations and what could be out there. And I think it's really a worthwhile exercise to think that through and to have the best case scenarios as to what could be out there. But we should expect that no matter what we propose, it's likely going to be wrong. And that's the point of the exercise to me. So I think that the case for building it now it's a question of the scientific case for the scientists as opposed to the spending money case for the politicians. The case for the politicians, the building of it is really, it's the building of it that's the useful thing, and the attracting of people to it and the spin-offs that come from it is useful. So it doesn't matter for them, I think, at some level. But they have to believe, as Martin said, that they're doing something where it's not going to be a white elephant where they'll be really ridiculed 10 years from now for wasting money on that. Why did they do that? So I think it's true that as physicists, we should decide, and it's not an easy question as to whether that's the best case forward at this moment in time. Given that the timeframes are so long, I think it's probably true that we should have a component of our effort which is aimed at extending our energy reach, and that probably also means extending research into accelerator techniques so that we can get to higher energies more efficiently and more cost effectively. But that should definitely be part of our program. But that may not be the highest priority part of the program now. And maybe, I don't really know what the answer is. It might be true that this might be the golden time to make a push in underground physics, or I think that those cases need to be made, and it's the burden's on us to make them. But I think they're completely makeable. So I have no doubt about that.
It's very interesting what you say, because I think I worked in the field, I see it as when you're making, and Martin, you'll know this being closer to the funding, I see it from a point of view of, do we have a good physics case? But when you're making the sell to a funding agency, that's not necessarily the biggest part of the problem, right? So
it's got to be there, but it's not the only thing.
Yeah. It's interesting. Something you kind of mentioned there, or at least alluded to there, Cliff, and I want to come to Varvar on this because I know you're a little bit in and out on this. Would a sensible middle ground then, if you've got people complaining, we're not really sure what we're looking for if we go up higher in energy, but you have this use case of a lepton collider where we're going to do precision studies of the Higgs, then would a useful middle ground to kind of help the kind of pill go down to build something like a muon collider where you get a situation where you have that precision physics, or at least aim towards a muon collider where you have that precision physics with the leap in energy kind of for free? Would that be something that could potentially make a lot of people happy? I know you have mixed feelings on this project.
Well, so let me begin by simultaneously agreeing and disagreeing with Cliff. No, first, because I think
a quantum superposition of agreeing and disagreeing. Good.
Absolutely.
Right.
I think you said something super important kind of in passing, but it's true is that many facilities and experiments we build end up discovering fundamental things, but they weren't built to discover those fundamental things.
Yeah.
And I remember a few years ago at...
so I'm being a bit too prescriptive, possibly.
A couple of years ago, at Neville Harnew's retirement party, Ian Shipsey gave a wonderful talk about this with the huge list of examples, which I've all forgotten. But you can make a big list, and it's there. So I think that's very important. But with that being said, I mean, again, it's not the same. So it's true, of course, we don't know that there's nothing out there. You can't prove a negative. But we also don't have any currently indirect indications that there is or should be something, and that hasn't always been true in the past. Now that there should be something within the reach of the next collider,
and that makes people jumpy, right?
I mean, just because in the past there have been examples. The top quark, we did sort of know at what mass it was going to end up at, and then it ended up there. We've had right now. The fact that there aren't the indirect indications, that's why in the end these short-lived flavor anomalies generate so much interest, because of course the community thought, well, if we're going to get an indirect indication of where to look, this helps a lot. So I think that's one thing. And then, look, I think if the field wants to stay vibrant, you need discovery machines for sure. because you can do precision standard model physics, and even outside the Higgs, that there's a reason why people are proposing to build charm tau factories, and there's a vast range of precision science that we can do to map out the known particle standard model in exquisite detail. I think we should do it. We should do it, but we should also not kid ourselves that part of what makes the field exciting is the hunt for the new, because you also get on the experimental side a mix of personalities, which is pretty essential to get the experiments working properly. And so, but for me, the real question here is, can we get a discovery machine in parallel with the precision machine?
Yeah.
Can we go back? I mean, as Martin also alluded to, can we go back to having multiples of these things? Because if the field really becomes basically just CERN, if that's all it is, and it's just FCE followed by FCCHH, I mean, there is now a vast range of questions out there that that the best and brightest young people can address, often using very similar tools revolving around, essentially processing enormous amounts of data and using that data without even necessarily theoretical underpinning to discover fundamentally useful things, not fundamental in the same way that the Higgs boson is fundamental, but fundamentally useful in a way that the Higgs boson maybe isn't. But things that they can do on timescales of 5-10 years plausibly, and you're selling to them the idea, come into the field now, and by the way, by the time you retire, you're not going to have your discovery machine. Yeah. Well, that's really a hard sell. So I think on this one, when it comes to the muon collider, I mean, I wrote some skeptical things about it on Twitter in the sense that I think the timescales. Yeah. This comes back to my point, and Cliff again here is completely correct that of course politicians want knowledge transfer, sure, but the timescales for the muon collider to happen in parallel, in my opinion, rely on a massive uplift in retention in the field, because from an experimental point of view, we simply cannot sustain the current rate of brain drain and necessary retraining of people. This is not sustainable, and you see it frankly also in the delays being incurred in the HLHC experiments, and because it's a real problem. And I think if you want to start doing things in parallel, it's gonna hit you like a hammer. You see it with Dune, you see it in all kinds of places. And I'm not saying that to pick any open wounds. I mean, I have friends and colleagues who work on all these things, and it's tough for all of us. But the amount of time that experimentalists, maybe this part I should put a parenthesis. I should say, look, none of this is whining. Okay, I've had a very, very lucky life, and I've had a very lucky career. Frankly, I got a chance to be at the LHC as it was starting up. Now I wasn't working on the Higgs, I was working on flavor physics, but I got to participate in getting one of the LHC experiments, working, LHCb. I have very little to complain about on the personal level. So this is not like whining about, poor me or what have you, but it's simply factually the fraction of time that us as experimentalists have to spend retraining and replenishing skills that are developed and then lost because of the ratio of people who stay in the field versus who do not. As I say, it creates an unsustainable situation. So I'm sorry, I know I keep coming back to these kind of sociological aspects. But I think, unfortunately, you can't solve one without the other. And then, and if these problems are solved, we got the muon collider in parallel. I have no ambiguity about it. I mean, yes, please go do it. I wish, frankly, I wish the Americans would do the muon collider and the Chinese would go and do CEPC. I mean, the more the merrier, in a sense, because the field would become more vibrant. We'd have more competition. We'd necessarily be forced to retain more people because you'd want to complete your project before humans are human. So sure, I'd like to see that. I mean, who wouldn't?
Martin, what do you make of the muon collider? Is that a halfway house that can make everyone happy, where we can do precision physics and potentially a jump in energy and have a look at the same time?
I don't think it's a good replacement for a precision machine, especially not for what the plus minus machine would eventually measure. I would see the muon collider as if it needs a lot of energy for that, obviously, but its real advantages only come into play if you build a 10 TeV or so.
Yeah.
At which point you really test the standard model at energies that you haven't tested before, which needs to be explained because obviously if the LHC runs at 14 TeV, but the LHC has composite particles and what actually takes part in the interaction has always less than the 14 TeV that the LHC can produce for protons.
Yeah.
So the muon collider is of course extremely challenging because we have no way of cooling down muons and then colliminating them onto a beam before they decay at the moment. And again, I don't want to repeat what I said before, but this is an R&D project that should have been heavily funded for a decade now. And it's really good that people start picking up on that and think about this now. But Vava is right. They call it the muon shot, right? In analogy with a moonshot. It takes a similar effort. You would need to actually put a lot of money behind this and a lot of effort. And if the Americans are united behind this project, I have no doubt they'll get it running eventually. I think it's a fantastic project. Its timescales are definitely more promising if compared to FCC HH. And again, I agree with Wafa to the point that competition is crucial in all these endeavors. If nobody else is going to work on something apart from a group of people that want a muon collider, it's more likely or not that it's not going to be built eventually. I think this is important. That CERN needs its project, the US needs its project, and if other countries want to join this kind of research, they need their project as well. What concerns fundamental discoveries, I think particle physics did themselves no favor that what counts as a fundamental discovery in our field is basically discovering a new particle. There is no other field that thinks like that. There is no other science that works that way. Yeah. It's nobody in astrophysics expects to discover dark matter directly with the next telescope or to measure something for sure that has never been seen before. We have a kind of double standard there. When the James Webb telescopes measures parameters that enters the standard model of cosmology, everyone happy and treats it as a success. This is also true for other projects, for satellites that we send to Pluto, or for other science experiments that we have done. In particle physics, if you don't have basically a guaranteed new particle that you can discover, it's not being considered as a discovery. Which is just not true. Understanding the standard model at higher energies, seeing whether it really behaves the way it predicts these interactions to happen, measuring the Higgs potential. These are all fundamental discoveries. They're just not called, they're not a separate particle.
And it's information for the theorist, right? If you know there's nothing there at that range, then that constrains certain theories.
Yes, it constrains certain theories, and also you measure something, and you measure something that might well be the standard model, might well be not. But again, it's basically semantics at this point, but it's being expected that what a new collider discovers is a new particle. Otherwise, it might not be a success. And I just don't see it that way. I think the name particle physics to begin with, like Cliff said at the very outset, it's already questionable where you draw the lines for that, right? Yeah. Well, what is a particle? What is not a particle? What counts as particle physics and what not? And obviously, there was an era where you discovered another particle every other week. As we said, not everyone was happy with that back in the day either. But based on this, the expectation has grown that this is what counts as a new discovery. And it's also not true that LHC has not discovered anything since the Higgs boson. We have learned a lot about QCD. We have measured WAFA, and LHCb has measured branch ratios and decays that we have never seen before. These are all discoveries. We just need to explain them that way.
Even particles, we discovered pentaquarks.
Yeah,
but they don't count.
Exactly.
Yeah.
Composite particles.
All right, I'm gonna have to keep it moving on. Cliff, you're going to be coming in strong in the next section. So this idea that we can't justify building more colliders. Is this a real crisis? 10 being a massive crisis, or 0 being no crisis whatsoever? Vava, 10?
7.
Martin?
I stick with 6. That was my overall mark anyways. I didn't know we get to vote on the...
That's all right. That's right. You can go on the separates. So if you go 6, 6, 6, 6, it'll work out as 6 at the end anyway. That's fine. Cliff?
Yes.
Maybe I'm a 5 on this one.
You're a 5 on this one. Good. Right, Cliff, you're coming in strong on this one. So The next crisis people talk about is that fundamental physics and the theory framework underlying elementary particle physics has stalled in recent decades. Basically, we're stuck in the mud. We have. Go on. Yep.
I'm interested that you put up John Giudesi's picture right now as you make this case.
I actually didn't know who it was, but you're going to talk about this in a second. So the idea that gets kind of pushed around is that theorists haven't kind of done anything for the last 50 years, since QCD was dialed in. What do you make of this idea that particle physics hasn't made much progress since the 70s, since the theoretical groundings of QCD? Is this a real concern, and how seriously should we take it?
Not seriously at all. It's a Twitter specific problem. And the way you tell is, it has been true in the past that there are fields that have withered on the vine, in the sense that they didn't make any progress. And it's often true that when you lose the experimental feedback on a fast time frame, that's often what makes things wither on a vine. Okay. And what happens almost always is that there's a few people that have invested heavily in that for their careers, and they just do that till they die. But then everybody else who's ambitious and young does something else, because they want to, in a time frame that's relevant for a career or for a granting cycle or whatever, they want to make progress, they want to have impact, and they go and they vote with their feet. So it really is a marketplace of ideas, and the marketplace of particle physics is thriving. And you don't see people. There some people leave particle physics, but there's been no shortage of ideas and activity and the idea that it's somehow, sometimes that's argued to be there's a cabal of puppet masters who are controlling everything.
We're going to get to that. Don't worry. Ed Witten as Voldemort. I've heard that, these kind of things. So this idea that we're kind of stalled, it strikes me as, what is the correct rate of progress, right? Were we spoiled by that golden era of particle physics? We had many breakthroughs, and now we have a period of consolidation. Why are people saying now that we haven't discovered anything since the 70s?
I think it's what Martin said, that if your ruler is, did we invent a new standard model? Then probably no, but then the question is that a crisis, and does that mean we're doing it wrong?
Yeah.
What's a little bit hard to take serious about some of these criticisms is that if it were really true that particle physics was in crisis, and it's just because we're not thinking about it right, because we're lost in the wrong questions, that's a huge arbitrage opportunity, right? If you really have an insight about that, then all the other people are thinking the wrong direction, then you should get in there and make the progress yourself. And people do that. It's not like it's a monolithic research program that particle physics has. Mm-hmm. There's lots of different directions that are explored. Everybody has their own bet as to what is the most likely place to spend their time, because that's the most valuable thing we have is time. And some people are successful, some people aren't, and people often, there can be fashions, and it's often people following people who have a track record of having had success in the past, which is kind of a rational way to approach things, particularly if you're young. And so I don't see any grounds. If I had thought that particle physics was in trouble and everyone was doing it wrong, then I would do it right, and you'd be reading about me as having the great success. It just seems like it's complete non-issue. It's a nothing burger.
So some people, you work in string theory, Cliff. So some people have argued that.
I don't actually. I'm on the edge of it.
All right. Okay, you're on the edge of it. So maybe you can give us a little bit from close to it. A lot of people argue that theory in particle physics is kind of a closed shop. You bend the knee to string theory nowadays, or you find it hard to make a living. You can't get funding. People don't take you particularly serious. What do you make of that idea? Because I hear that swirling around an awful lot.
I think that there's two levels of that. One, and so let me start with the part that I think has a grain of truth to it. And so the grain of truth to it part is that people complain that string theory's been around for, it's been around since the 60s, but it really kind of made a splash when I was a graduate student, which is a long time ago. and yet we still don't know if it's the right theory of quantum gravity. And at the time in the 80s, there was a lot of people were a lot of hubris. People who thought that we're going to really solve a lot of things very quickly. And I think it's true that hype wasn't realized. And I think it's also true that you could say that here's a theoretical direction that's been around for 40 years. And so why don't we know if it's true or not? And the thing that they're fighting, so the reason that doesn't bother me particularly is that, everybody who does quantum gravity is fighting the same thing. That the basic problem is the fundamental scale involved, the Planck scale, is super large compared to anything we have access to. And nature just hides small distance physics from large distance physics. And we normally like that because we'd like to be able to make predictions about atoms and not have to know everything there is to know about the rest of the universe right down to the Planck scale and still be able to make robust predictions. And so normally it's a good thing that we don't need to know what's going on at small distances when we make predictions at long distances. But if you think you know what's going on at short distances, it's a bad thing because it's very hard to make a prediction that's not just a generic symmetry prediction. And I think that, so when a condensed matter physicist criticizes string theory, saying that it's not making enough contact with experiment, I think most string theorists would agree that we would love to be able to be doing what the condensed matter physics people do, interact at that level with data. But when other quantum gravity people make the criticism of string theory, then it's kind of a bit of a pot calling the kettle black story where everybody's in the same boat. Nobody's making any great predictions because they're all fighting this decoupling problem. And so then I think it's really not so compelling. And my take on it, because I'm not a string theorist, is I'm interested in questions. If you did have a theory of quantum gravity, what could they teach me about particle physics or other things? And I find that that's taking me to string theory more often than anything else because they've gone farther in the sense that, in my assessment anyway, that they have kind of crossed a series of tests that other quantum gravities haven't. It doesn't mean they can't, and maybe they will in the future. But you can ask questions in a very crisp way with what the string theorists have done because they've gone so far. And I think that's what they've achieved. And so the idea that somehow there's a you have to bend the knee to them. I think what's really happening is it's a marketplace of ideas, and they're winning, and they should be acknowledged for that. And it's true that doesn't mean they get a free pass.
There's a place for dissent, though, right? The idea seems to be that there's no dissent, and you either go into that or you don't go into anything.
Which is not true. I mean, the people that are often complaining are not string theorists, and yet they're still funded. so it's kind of hard to know how that works.
Good, Martin. Another thing that we get on the theory side as to why it's in crisis supposedly is that theorists are kind of lost in complexity. They're lost in maths. They're too eager to patch up old hypotheses like Susie when they don't pan out, particular experiments to tweak parameters, rather than keeping models simple and economical. What do you make of that accusation as a theorist, Martin?
I have to ask. I don't even know what precisely is meant by being lost in math, to be honest.
So you'll be talking about axions, you'll be talking about supersymmetry, repatching up supersymmetry, changing parameters, rather than following the data and admitting that we didn't find it and going with a simpler model.
Yeah, that of course depends on what you're looking at. So if you the motivation for supersymmetry were manifold. They were not necessarily motivated from like low energy constraints. They were, for example, string theory that would need supersymmetry to work the way it was envisioned in the 80s and 90s. So there were a lot of fundamental reasons to go there, and that you could call that lost in math, I suppose. But I would say this is motivated by a more fundamental theory that we have worked out and understand. If you say that we should stop looking for something because we haven't found it yet, you can make that criticism at any point in any time when you look for something where you have a parameter space that you can look for. I think an important point that should be made is that we have a framework that's not string theory, it's quantum field theory, that is already enormously constraining. You can't just go out and say, "Oh, let me add something over there," and I change that. When you Newton,
you can, but it doesn't make any sense, right?
It's mathematically not consistent. I mean, this constraint to be mathematically consistent has becoming more and more constraining over time. If you were Newton, you might as well just write down a potential for gravity that contains some sine function or something more complicated. There's no reason why you wouldn't. But if you derive the potential from a quantum field theory calculation, you're basically pinned down by the fundamental parameters of the theory and the kind of spins particles can carry, the kind of types that are allowed by the fundamental theory. So we know all that. When we say we look for an axion or we look for a certain particle, you can already take the point of view that the number of things that you can add consistently to the standard model is fairly small in the range of possibilities. And we know that this is the case because we know the quantum field theory is incredibly successful everywhere it has been tested ever so far. So there's good reasons to believe that the world is described by quantum field theory at fundamental scales, the ones that we can reach at the moment. And if you want to modify them, you have to play by those rules. So this has nothing to do with.
So it seems to be a bit of a faux idea. The idea that's presented is just kind of particle physicists come up with these randomly named particles, axions, WIMPs, sterile neutrinos, whatever it is, and they just kind of pull them out of their backsides because they need to get a paper out, and then they go looking for them. But this isn't the case, is it? They're constrained already by particular aspects of the theory, and also you wouldn't be allowed to go looking for them if they didn't fit into a new area of parameter space that we need to clear off. So I know you do some, or you're looking at doing some work with Anubis, which is looking for particles that decay further from, the interaction point, for example. That would not be funded if it was just particles that you would have expected to see already. So when you come up with these new particles, they're usually in a new part of the parameter space that we haven't looked at. It's not just people making up different types of particles to go looking for and then not finding them. Martin?
Both those things, I think.
Well,
yeah, it should be said that one consequence of quantum field theory is no matter what modification you do, it comes with a new particle. It's not like you add the new particle and that's because you like to do that. You can't modify the theory by any kind of new force, new extension, new field without, as a consequence of this prediction, and get a quantum of that, which you would describe as a particle. So these things don't emerge because people like them so much. They emerge because any kind of modification that you would do to that framework gives rise to something like that. And it's one way of looking for them. And it has been a very successful way of looking for them. Doesn't mean to be right. Axions, for example, are not only searched by particle physicists at all. There are experiments at all different scales where they can act like classical waves, or where they basically, where you would not act like a particle at all. You wouldn't describe them that way within the experiment. But in order to be within the framework of a quantum field theory, they also have these properties if tested at the energies at which you could produce them. So that is just a consequence. And this is just a fact. That theorists give particles silly names is historically also true. That has nothing to do with whether they exist or not. If that was the case, there was a bunch of particles in standard model that would have never been discovered.
But people inside the field realize that there are different areas of the parameter space, right? This is why we have the forward physics facility now at CERN, for example. If this cost the same cost as another LHC, we wouldn't be building it. But we can close off these areas of the parameter space at relatively low cost, right? These are things that are taken into account in the field. It's not just people in theory throwing out particles and going, yeah, we'll build that. It's really expensive, but who cares? We'll just build it because that sounds good, Martin. That's not the case at all.
Yeah, it's an interplay between things that can solve a problem, so they are theoretically motivated, and opportunities that are experimentally motivated. If I want to understand what the Higgs decays into, and I want to test whether it decays into something new, I need something that produces me enough Higgs bosons so I can test these decays. And we have something right now. We have the LHC. So if I build a far detector for a long-lived particle, for example, I have the opportunity right now to do that for the price. I won't have the opportunity for the next couple of decades if we don't have anything that can produce the Higgs bosons to do that test, right? So you probably wouldn't build the LHC from scratch plus this detector if you were in that situation. But because we have the LHC in the first place, we have the opportunity.
These are auxiliary experiments that extend the reach of the kinematic space that we can look at.
Yeah, that also goes along with what I mentioned.
Of course, Cliff, please. Sorry, Martin.
Sorry, Martin, finish, Martin. I'll jump in after you're done.
Martin,
just to finish the thought, because that also goes in line with what I said previously, that big experiments like universal case experiments like the LHC, have use cases that you might not even envision when you start them up. What Phaser, for example, does, that forward facility you were talking about, independent of all potential new physics cases you could make up for it, it also tests neutrino scattering cross-sections at scales we haven't seen before. In fact, the anti-tau neutrino hasn't really been discovered directly. There's never been one produced and detected at any machine. It's the last standard model particle that hasn't been seen. It just isn't as famous as the Higgs boson. And now the forward facility has actually seen it, or the Phaser experiment has seen it. They have a couple. So the original experiment that discovered the tau neutrino, I think they had a handful of tau neutrinos, but they never had an anti-tau. So this is the first experiment that sees it. It's if you want to discover new particles, there's another one that the LHC has discovered, and that certainly wasn't built for that case.
Cliff, did you want to come in?
I wanted to add one thing, just because I completely agree with what Martin said, but there's a way you could interpret it, which I know that he didn't mean, and I want to make sure that it comes across, and that is that, he's saying that there's well-motivated things, and you were saying that people are not just making up particles. Some people are making up particles. And I think the way to think, and that's a good thing that they do, in the sense that I think most people aren't, because it's not the best motivated thing. But it's not like there's an orthodoxy that says if you want to make up particles, you can't do it. It's a risk portfolio, that there's some things that are very likely to be successful and are less, but probably not going to revolutionize what we know. There's some things that are very out there, and people will do things that you can't do in quantum field theory, and they will hold a nose and do it anyway. And normally they fail, but the thing is, it's good that they do them. Yeah. But it's, I think the main message, which I agree with completely, is that these criticisms that it's complication for its own sake, that's not true, because what people are doing is they're working within the constraints, some more than others, but they're building in the constraints when they take their risks, and the complication is not really what's driving it, or the simplicity. If simplicity is all we needed, then show me the money, show me the simple theory that everybody's missing.
So
yeah, surely the standard model, if it's anything, it's not simple. It's the worst possible example for that guidance.
So Cliff, theory has stalled and we haven't done anything since the 70s. Is this a crisis, 10 out of 10, or is this no crisis, 0 out of 10?
0.0001.
Martin?
Yeah, that 1 out of 10. This is the least critical factor that you have on your list, I think.
Vava?
I'll give it a 2.
You got to go higher because we're experimentalists, right?
I gotta go higher.
Pump that up.
I'll give you a sentence to go with my 2, which is that it's hard to look at the enormous number of models and theories that have been conceived of to predict what is beyond the standard model, and kind of go, oh, well, this is stalled. Certainly saying it's stalled is. On the other hand, it may be the theory is currently in a very unfortunate relationship with what is experimentally probable. In that case, you could, I suppose, interpret that it's stalling. Hence my 2.
Good stuff. Right, we're into the last 15 minutes. Vava, you're going to be strong in this section. So the final crisis I see is kind of that particle physics has an image problem, particularly with kind of people who could be excited to come into the field. And there's these structural problems, which Vava has mentioned, which are impacting our ability to attract and retain the best and brightest. So Vava, you mentioned that the kind of construction lead times of projects are becoming incredibly long. We have this incredibly high churn in the field, and people can't really expect, and we also have uncertainty in what we're going to find. So people can't necessarily expect to work on a discovery machine within their lifetime. If these are such massive problems, and I agree with you that they are, how do we go about tackling those problems?
So I think, first of all, we should say that when there are problems, if they happen in large systems, often you see the effects of the problem, like you really feel the effects, particularly catastrophic ones. It can take a long time for them to percolate because large systems have inertia. And so it's not, if things start being problematic today, there might be a long period of time where you think, okay, but it's not really that bad. And then it hits you.
You mean like climate change?
Well, for example. So I'm just saying, like, but there's definitely, here's a few factoids, right? When I started as CERN fellow, my supervisor was super proud to tell me that every single person who worked on this North Area experiment back in the early 80s got a permanent job at CERN. There's no experiment, no matter how big or small, where that happens today. Okay. If you look at the salaries of French public sector researchers today compared to general salaries in France, and you look back what that was in the early 80s, you see that there's been a near factor 2 collapse in the ratio. Okay. That's France, because I happen to know the numbers. But I think in general, when you look at the kind of careers available, especially to prospective experimentalists coming out of high-energy physics, the field's not at all competitive on that. And the sacrifices it expects people to make for the cause are growing, they're not shrinking. So those are like small factoidal problems. But then we should also recognize that those problems don't hit you at the PhD student level. And one of the reasons why the field, I think, is still going very, very strong is because it's a very attractive place to do a PhD. I don't think the field really has any problem attracting. It might have a little bit of a problem now with AI, let's say maybe in the last 5 to 10 years, but it's not yet critical. But attracting super bright people to do PhDs is not the hard part. But then on the experimental side, though, what many, and I mean, you can testify to this as much as I can, what many very quickly realize is this is a highly corporatized environment, the big experiments. And, again, I've done my whole career on an LHC experiment, so I have obviously a very biased reference frame from that point of view. But within that, within CERN, within the LHC and so on, it's a highly corporatized experience. It's not just about not getting a discovery machine. I mean, you have to be comfortable being a small cog in a very big wheel, which reduces, compresses in some dimensions, compresses, in some dimensions maybe expands the kind of range of personalities that you're going to attract. But definitely it changes the mix. And then you're also faced with a very long time period of uncertainty, which has hugely problematic effects for, in particular, people who are from marginalized groups or from, underrepresented groups or from poor socioeconomic backgrounds. I mean, because again, the alternative is a lot more stable, a lot better paid. At least it feels that way in the short term, the more stable part. So there are all these real problems. And so retaining post PhD, the best and brightest.
What would be your prescription to?
This gets harder and harder.
Make sure we can do that.
Well, I mean, there's no magic bullet. You have to be willing to not run a high turnover model. I mean, there are companies that run high turnover models, but Google can get away with a high turnover model because you get a Google job. First, you're paid very well, and secondly, it sets you up for life, CV wise. So you get what you want out of it. But then on top of that, they're hiring people who are, qualified. They're not hiring people where they have to spend the entirety of the high or a large fraction of high turnover period providing them on the job training. We run a high turnover model in experimental high-energy physics without those benefits, or without at least some or many of those benefits. And as I say, in the long run, that plus the hyper specialization, because you're now in a collaboration of 3,000 people, so you get to see one small part of it. There's very few generalists. Certainly in my generation, there's very few people who could legitimately claim that they could do like every bit of an experiment. Whereas in previous generations, you legitimately have large groups of those people. Okay, I just don't think now I can try to come up with a bunch of smart things. But unfortunately here, I think the simple thing is the truth. We need to be able to retain a significantly higher fraction. So it doesn't have to go back to where it was in the 80s. Life isn't black and white, but it needs to go up. The retention has to go up, I think. And no matter how much we play games with, we can do as much as we want, joint programs with interdisciplinary things or private, joint work with private sector companies, etc. This gets you so far.
You mentioned potentially reverting back to 30 to 40% PhD to tenure rate.
Well,
the understanding of,
I mean, that's what was, by the way, when the field was growing up, that's what was sort of considered to be like an indicator of a healthy field. Now society's changed. So funny enough, Martin, your quip about the fact that back in the 80s you'd have to like steal the wealth of 5 of the richest people to build the lab, and now it's like a fraction of Elon Musk. There's a broader point here which that illustrates in the relationship between the public sector and the private sector. And these things are all interconnected. No, I think 30-40% is a fantasy, which would be nice to get back to. But even if you could increase it at all, it would clearly have a positive effect. How to get away from the hyper-specialization is hard. But again, if you weren't so short-staffed, and if you weren't short-staffed also in the sense of being staffed so much by students who you're kind of supervising, maybe people could do smaller experiments in parallel with bigger ones. I don't know. I'm not here selling that there's some, unfortunately for your podcast, where I do realize the format appeals to pithy one-line solutions to massive problems, but I haven't got that to sell. But I think burying ostrich like our heads in the sand about this, my theory colleagues, I'm afraid, might be disappointed what comes out of that.
So there is a real problem as the timelines get longer, as we're not necessarily sure what we're going to find, as we have this high turnover. There's a difficulty, and I know we're coming up to Cliff's hard deadline, Martin. There's a difficulty of keeping good people in the field, both in experimental and potentially in theory. Martin.
I think that's not wrong, but these are changes that the field has to make overall, not just this field, by the way. I think academia in general, not all fields to be clear, but especially in the sciences, is a very competitive field. It asks for a lot. It asks to travel. It asks to take on positions for a short time scale in different countries and then move back if there is an opportunity. You write applications all the time. It is, in my opinion, not bad that there is competition from industry. It shows that when we teach people, when we educate graduates, that they are sought after, that they can go into these jobs. When I did my PhD, which is not that long ago, the people that went to industry, they were mostly interested in going to banking sector, maybe insurances, maybe consulting companies. There's been a whole different field now in the last couple of years where people can work at the tech giants. It will only grow with AI. Where physicists are being sought after because the way we solve problems is exactly the kind of way you solve them there. And this is also going to be true for experimentalists. Like the LHC are the original big data people. They are perfectly well suited to take on some of these jobs. And this competition is good to change the field. If we want to keep people in the field, we have to make these changes. That is also true for women. If you have to travel the world between the time you graduate and you maybe get a permanent job 6 to 10 years down the line, but that completely overlaps with the time you usually plan your family, then you don't need to complain that in the end it is very hard to retain excellent women on the job. So I think these changes are necessary anyways, and we should do them rather sooner than later, but they will come with sacrifices. So it's not going to be an easy transition, I think.
So this seems like it is potentially something we really have to think about. Vavar, a score on this one?
Can I jump in before we score?
Yeah, of course you can. Please, Cliff.
So I just would like to make 2 points, because I think I basically agree with many things, but I think that this is really a policy issue, and it underlines something we've talked about before, which is competition. I think that my experiences, which has not been extensive in granting agencies, it was been in Canada, and there you can kind of see the experimentalists make their choices, and there are big collaborations like the ones at the LHC, and then there's smaller collaborations that are like the ones at Snow Lab for us, and you can see experimentalists, according to what their tastes are, choose differently when deciding which ones to join. And so having them available is part of the policy things that we want to have, is we want to have a diversity of options for what we build, because we want to be able to have accommodate people with different kinds of tastes in what they do. And it's also true for salaries, that countrywide, that if academics are paid poorly in France and they're paid well in Germany, then they will go to Germany, and then the French will miss them and will pay them more. So I think having competition, which we talked about before for accelerators, is also going to play a role in this. And as far as retention goes, I think that the thing that I would see there as being, as a policymaker, is important, is that there's one question is turnover for junior staff, but another thing is retention of core competence. And so the thing is, you can make the case for there being a lot of turnover in junior staff if you have a core of expertise that you're not losing, because you're losing actually the people who are training the junior people. And so it really is true that you want to make sure that you're not losing that you're keeping the institutional memory of how accelerators work and the things that you really need to do to run these big things. And it reminds me, when I was a student, I was across the hall from John Wheeler, and I remember at one of the departmental functions, somebody asked him, "How do you get the Texas billionaires to fund research in general relativity?" And what he said was basically, these physicists are a strategic resource. That he said that when his experience during the war was that when you needed radar or you needed some sonar or some new thing, it was the physicists that came up with the new things. The engineers, you needed them too, but you didn't just have the engineers. It was important that the physicists were there to help crack the codes and do all these things which are really hard to predict what you're going to need in the future. And at some level, keeping the core competence, and particularly in experimental, but also in theoretical physics, has that character for Western societies, or all societies, I think. And that's I think a killer argument for when you're making these cases to the funding agencies, is that they see that infrastructure and people strength side of the argument.
Yeah. And I think that's something that often gets overlooked. So I'd like to thank you all really very, very much for taking the time. I really, really enjoyed it. Some new perspectives that I hadn't thought about. And I will make sure that gets edited up and released tomorrow. So again, thank you very much. I'll make sure all of your links, all of your work are down below in the description. And thank you very much for taking the time.
Thank you very much. It was a lot of fun.
Nice to meet you guys. Bye.
Absolute pleasure.
Yeah, good to see you.
Take care.
Yeah.
I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.